Hello everyone, welcome to this presentation here where we're going to be talking about how we can use S-Frame to generate for us a map foundation panel, and what that will do is will generate for us a shell element mesh representative of the material properties of whatever we've assigned to that panel. And when we mesh that panel, it's also going to allow us to generate or enter a subgrade modulus, which will then facilitate the creation of ground springs underneath each node based off the tributary area of each one of those joints. Now, to get this process started, I want to make sure that when I'm modeling this, I'm using this map foundation panel. So you'll notice I actually have two different panels in this model. I have an area load panel on the top and a map foundation panel below that. It's available under the panel elements tool. If you don't see this legend here, you can also grab it from the panel type drop-down list in the data bar. Or if you want to display or remove this legend, just toggle on this display legend button at the bottom of the screen in this status bar to make that available or remove it. And what's going to happen when we go ahead and mesh our map foundation panel is that it's going to prompt us to enter a modulus of subgrade reaction. So this little dialog appears when I clicked on the mesh panel elements icon here. And it's going to ask me for a modulus of subgrade reaction. So let me add a value here. I'm just going to say that we have a value of 10,000 kilonewtons per meter cubed. And you'll notice that we have the option here to generate different spring types. Depending on the addition of S-Frame that we have, we can generate compression-only nonlinear springs, which will have stiffness and compression. But if they go into tension, they'll not have any stiffness. And I can also generate linear springs. I'm just going to go with the linear springs option for now. And I'm going to click OK. And you can see here that the mesh has been created for us. I'm going to click the Yes button to view my mesh, and I can now, maybe what I'll do is I'll turn off the rendering, and I can just study this mesh a little bit more closely here. So here I can go in and see things like the spring properties. So if I click on the ground spring tool, I can see that's generated ground springs in the Z-axis, and I'm now able to look at the spring stiffness for any one of these joints. And you can see here that it's varying depending on which joint I'm looking at. So joints that might have a larger tributary area are going to have a higher stiffness portion to them. Joints along the edge are going to have a lower stiffness because they're only attached to the mesh on one side. And the same thing we'll notice on the corners, that we even have a lower subgrade modulus, or spring stiffness rather. Now let's just say, for example, that we want to run this analysis. We could go ahead and run this. I've already applied some loads. So now I'll go to the linear static analysis. And we're running an analysis here, and the solution trail that's come out of this is showing me here that I do have some diagnostic messages. I get these K-negative definite messages, and it's indicating to me here the node 297 and two different degrees of freedom. So degree of freedom 2 and degree of freedom 6. Now I haven't actually introduced the loads that I have, but for your information, they're all in the vertical direction, basically the Z-axis. Degree of freedom 2 is indicative of Y translation. Degree of freedom 6 is indicative of rotation about the Z-axis. So these are two directions where I have instabilities, but I don't actually have any loads that would induce any sort of action in that direction. However, it is letting us know for our information that we do have instabilities in those directions. If we wanted to get rid of those messages, we could apply perhaps a small spring to different nodes in our mesh in order to prevent that motion. However, in this case, I'm not going to worry about it right now. What I will look at here is the deflections. So I can see how the structure is deflecting. We can see that there's some downwards deflections in this map foundation panel. I can also look at my reaction loads, and naturally we're going to see kind of a varying distribution of reaction loads due to the applied, I have a pressure load applied to my map foundation panel. I also have area loads applied to the roof above that. And you can see the overall reaction. And when we use a map foundation tool, we can actually look at the soil pressure contours, and I can see the soil pressure distribution throughout my pad. I'm using a unit that maybe doesn't really illustrate this very well, so let me just change my units. And we can see how that soil pressure distribution changes throughout this pad. One last thing to consider is that we may need to make changes to our model. Perhaps we're changing the layout of our columns, Or maybe we're changing the mesh. And if we want to do that, we would do that just in the same way that we would delete any other mesh. We start by deleting our shells. So I'm going to use a quadrilateral element tool since that comprises the majority of my elements. And I'm going to hold down the control button on my keyboard with that quad element tool selected and left click and drag. And you can see here actually it looks like I'm using 100% quadrilateral elements, so that saves me a step. I'm left over with these nodes, these joints, and these joints actually have springs attached to them, remember. So we need to get rid of those joints. So I'm going to use a joint tool. I'm going to use the same command, hold down control with the joint tool, left click and drag. And something that's worth noting here is that the springs that were generated during that map foundation meshing were generated on all the joints that were produced during the meshing operation, but also in other joints that may have already existed during that operation, including my seed nodes at the base of my columns and the vertices of my panels. So if I just display my springs again, I can see that I do still have springs on these joints that I should make sure that I get rid of those as well. We don't want to remesh and produce additional springs on those joints. We could end up with higher stiffness than we intended. So I'm going to use the spring tool this time, the linear spring tool, and just get rid of the springs on these joints. Now I can go back into my panel element tool, and using the map foundation panel, I might decide here I want to modify the mesh parameters of that panel. And in this case here, let me just go with a higher mesh density and perhaps even a higher seed density. And I'm going to apply that property to this map foundation panel. We can verify that it's been assigned by clicking on the mesh density display, so it's 25, and the seed density display as well. And at that point I could go ahead and remesh. It's going to ask me for my input subgrade modulus again. And this time you can see we've remeshed and we produced a finer mesh. It may not necessarily be required for all applications, but we do have control over that. And that's what I really wanted to highlight here. If you'd like more information on meshing and just FEA in general within SRAM, you can check out the other videos on our YouTube channel, but we also have a dedicated training course that's available on demand through the Altair Learning Management System. Thank you all, and look forward to seeing you in future videos.